Performance of transmission lines. In this presentation, we will discuss transmission line models and their equivalent circuits. And this is particular with short and medium line approximations or transmission lines, okay? Because there is another transmission line classification, which is the long transmission line. We will have that in a separate discussion. Also, in a separate video, we will show sample calculations of the circuit parameters involved in short and medium transmission lines. Okay, so let us start with transmission lines. That is, transmission lines are represented by the two-port network, okay, as shown here. So your Vs and Is are the following: the sending end voltage and current, okay, that's your VSIS, and your VR and IR on the other side is the receiving end voltage and current respectively. Okay, so in transmission lines we have it is represented by two-port network. We have VSIS, the sending parameters, and IR VR, the receiving parameters. It will always be like this. Now we have the sending and the receiving. The general equations, alright, regardless of what transmission line it is, okay, so these are the general equations. Vs is equal to AVR plus VIR, and Is is CVR plus DIR. Okay, or in matrix format, we have here the VSIS, ABCD, and VRIR. Alright, so that's the general equation and the general matrix format. Okay, equations and matrix formats of general transmission lines. The ABCD parameters, so try to recall the matrix format, okay, depend on the transmission line constants R, L, C, and G. So these parameters are already defined and discussed in the previous presentations, right? So R, L, C, and G. In general, these parameters are complex numbers, wherein your A and D are dimensionless, then your B has a unit of ohm, and C has a unit of Siemens. Okay? These parameters apply to linear, passive, bilateral two-port networks, and they follow this identity. AD minus BC is equal to 1. Okay? So every transmission line, short, medium, and long, has ABCD parameters. Okay? So since we have three types of transmission lines, alright, we'll have several ABCD parameters. They have their own ABCD parameters, which are unique to each type of, or each approximation and type of transmission line. Okay, so for short transmission line approximations, so a short transmission line is an overhead 60 Hz line that is less than 80 kilometers long. Okay, so we consider that as a short transmission line. So beyond 80 kilometers long, it's another type of transmission line. It only includes series resistance, okay, so series resistance and reactance. And the specific reactance here is inductive reactance. Okay? So there is no series capacitive reactance. Okay? Wala yun. Okay? The shunt admittance is neglected. Okay? And the circuit is shown here. So the sending end, the receiving end, and this is your impedance. Only the series resistance and the inductive reactance in series, okay, are considered. this short transmission line can be applied to either single phase or completely transposed three-phase lines. And our assumption is they are operating under balance conditions. Okay? So, parang transposed na sila, na-balance na sila. Okay? Okay. Your Z is the series impedance. And this is applicable for both the single and three-phase, okay, lines. Now, for three-phase lines, your VS and VR refer to the positive sequence line to neutral voltages, okay? Kasi kapag series lang siya, automatic VS, VR, this is the line to line, okay? Line to line siya. Kasi isa lang naman yung line eh. I mean, from line 1 to line 2, that comprises the single phase line already. Okay? Whereas, for three-phase lines, diba? So, automatic that your VS and VR in our general equations are considered the line to neutral voltages. Okay? Because in our previous calculations, diba? In our previous study, even the inductive reactance or the inductance itself and the capacitance itself of three-phase lines, diba? We only needed the one phase. We only need one phase, okay, for our analysis. So the same thing here, no? So our VS and VR quantities are automatic to be line to neutral voltages. So that's our base assumption, okay? Unless otherwise, I guess, mentioned or specifically mentioned that the given VS or the given VR is something like in line-to-line quantity, no? As a line-to-line quantity, okay? So the same thing with IS and IR for three-phase lines. Okay, so these are positive sequence line currents. Okay, so please take note of that no, because we have a different notation for VS and VR. These are line to neutral voltages, and your ISR are the line currents. Okay. Now, there is a notation that's being followed. Okay. So that we will not be prone to using incorrectly, no, or the wrong use of the total series impedance and the series impedance per unit length. Okay, so for example, in our previous calculations, we express the L, for example, diba, the L in Henry per meter. Okay, so pag kinuha natin yung inductance niya, inductive reactance, rather, it will be always in per unit length, no? So, like, ohm per meter. Okay? So, in this case, these are not the notations that we will follow. Small z will refer to the series impedance per unit length. Okay, so that is in ohm meter. Whereas the capital Z will be your total series impedance. So in this total impedance, we have factored in the line length. Okay, so may line length na siya. So from small z, which is ohm per meter, okay, multiplied it to the line length, which is a meter, will give us the ohm. Okay, so that is small z and capital Z. Okay, actually, even the shunt admittance, alright, follow the same notation, no? When we have our small y, it means the shunt admittance per unit length. Capital Y refers to the total shunt admittance wherein the line length is already factored in. Okay, so these notations apply to other transmission line models. Okay, whether it's medium or long transmission lines, we follow the same notation, no? So please take note of this, no? The big difference between small z, y, and capital Z and Y. Okay, I hope it's clear. Now, going back to short transmission line approximations. So, here are the general equations, okay, which are unique and applicable only to short transmission lines. Okay, clear. We have Vs is equal to Vr plus ZIR. And Is is equal to IR. Okay. Actually, these equations were easily obtained by simply applying KVL and KCL in this circuit, no? Simple KVL and KCL, and then you will arrive in these equations. Okay. Now, in matrix format, we can observe that from these general equations, A here means 1 and your B here is Z. Okay? Remember the general equation and the matrix format of the general transmission line model. So we have here, diba, the A, B, C, D. Okay? So from the derived general equations of short transmission lines, so we can see that your A here, which is associated with VR, is 1. This is your B, is Z. And for IS, this is your, there is no C. Okay? There's no C. And your D, which is associated with IR, okay? So D is 1. Okay? So the ABCD parameters of the short transmission line are the following. A and D, both are 1. Your B is Z, and your C is 0. Okay? So all these pertain to short transmission line, and we use them when we analyze the performance or determine the circuit parameters of short transmission lines.